Hello guys, thank you so much for being with me in another video of machine learning tutorial. In the previous video we explained some existing definitions of machine learning. We introduced the game of checkers and said that Arthur Samuel had tried to write a program that got better after playing it millions of times and learning from mistakes, and despite the fact that it was defeated by Samuel himself at first, it was able to improve over time by generalizing its experiences. Defeat both Samuel himself and other players. We said that this generalization capability is one of the most key capabilities of machine learning. We also presented a more formal definition of machine learning and talked about the task efficiency and experience criteria, and examined the example of spam detection. And we said that we do not provide an exact and explicit definition of spam. We said that we have three methods of machine learning, and in the previous video we talked more about supervised learning, and we said that we have a set of ordered pairs. For each input we provide the expected output to the system. We call this type of learning supervised learning, and we said that in this type of learning we seek to learn a function to map from x to y. Here we have an example of recognizing handwritten digits. Here we provide the system with a set of handwritten versions of numbers along with the corresponding number. Another example for supervised learning is predicting whether a tumor is benign or malignant. The output of this mentioned function can be discrete or continuous. For example, in these examples, the outputs are discrete. In cases where the outputs are discrete, we consider the problem a classification problem. But for example, let's assume that we can determine the price of a house based only on its size. We provide a training set including houses whose size and the price we know. We said that the computer does not have the ability to distinguish between numbers that are different from the 16th decimal place. So in this example, the output is considered continuous by the computer. These problems in which the output belongs to a continuous set are called regression type supervised learning problems. In this video, we want to talk more about these types of issues. As we said, the size of the tumor is not the only effective factor in whether a tumor is benign or malignant, and various other factors are also effective. For example, let us consider the patient's age here. We have marked the output with the symbol X and O. In this video, we will learn how to get borders so that we can classify the data according to their benign or malignant. Determining this boundary in real-world examples can sometimes be very difficult. For this reason, there is a need for complex computer algorithms. In these educational examples, we have simplified in several ways to make the content understandable. We have discussed this in the previous video. Suppose the outputs are not specified. For example, we have a series of two-dimensional data. We call this unsupervised learning. There is no information about the y's. In some cases, there is a structure. For example, we look at two-dimensional figures and see that some data have a smaller Euclidean distance, so they will probably be placed together in the same category. A machine can do this. This type of classification is called clustering. This is done by the system itself. So in unsupervised learning existing structures and patterns is only by having a set of X. That is, here the training set does not include Y and X, Y and X, but we have only a series of X which are clustered based on their proximity and similarity to each other. The interpretation of what these clusters are is up to humans, and the computer has nothing to do with the meaning of these clusters. This is called unsupervised learning. Consider the example of grouping related news. It must have happened to you that you searched for news on Google. In addition to the news that it provides, it also gives you a series of other links that contain the same news from different news agencies. The sentences are different, the news sources are different, but the news is the same. How does Google know that these news are similar? Google itself has understood this similarity. For example, there is a criterion for measuring the similarity of two news items, and that is the number of common words in those two news items, for example. Unsupervised learning has many different applications. Social networks are very popular. For example, on Facebook, people become friends with each other and form a graph. Every user who uses Facebook may have different activities such as comment, like, install Facebook recommended applications. Facebook gradually learns which users have similar interests and clusters them. Then, during the intelligent advertising based on these interests, it will display the ads of interest of each group to the users in that group. One of the main tasks of Apple and Samsung companies is to cluster users in order to target the market. For example, there is a group of users who are only looking for cheap phones and don't care about the functionality of that mobile phone. So when producing an expensive phone, it does not send relevant advertisements to this group because excessive and irrelevant advertising has the opposite effect. So to avoid this reverse effect, the companies are interested in targeted advertising, which is possible under the shadow of clustering. Unsupervised learning and clustering are also used in astronomy. From here on, we'll move on to supervised learning, classification, and regression, and we'll delve deeper into unsupervised learning in future videos. This simple question is asked to summarize. In the first problem, it is obvious that we have a supervised learning problem. The second problem, is clearly an unsupervised learning problem because no one has told Google what topic each article is related to. The third problem is a precisely supervised learning of the classification type. We want to move on to problems in which the output set is continuous. We start with the simplest type of regression. Okay. Let's dive into the Regression C. Okay. We explain what linear regression is. In the following, we will learn about the very important gradient descent algorithm and see how widely used this algorithm is despite its simplicity. Then we will check the corresponding mathematical method, and then we will compare these two methods. When we introduce two methods to solve a problem, it means that these two methods each have advantages and disadvantages that we will examine. Let's go to the example of predicting house prices. We said that the inputs, the horizontal axis or the x-axis is the size of the house. We have recorded the expert price of the houses in the y-axis. Now we want to learn a function that maps inputs to outputs. Now that we have this function, we can predict the price of a new house based on its size. One of the examples of regression is a location. What we want to specify in this problem is a bounding box that specifies where the location of this object, tiger or cat, I don't know, this is a tiger or this is a cat, is in this image. Look at the green box in the picture. Consider the two opposite corners of this rectangle in coordinate axis. Each rectangle can be represented by the coordinates of the two opposite corners. For example, the upper left and the lower right corners of each corner have their own coordinates, and each of these numbers belongs to the set of real numbers. So this becomes a regression problem. Here, what the system has predicted is the red rectangle. As you can see, there is a slight error. Another way to show a rectangle in coordinate axes is to show a corner and the length and the width of that rectangle. We have used the second method here. So the first two numbers are related to the coordinates of the upper left corner of the rectangle, and the next two numbers are related to the length and width of the rectangles. So now we have to predict four numbers because these numbers are real. So it is a regression problem. Let's go back to the example of the house. Here, because our training set does not have output values, the problem of learning is not supervised. In this lesson, we have a series of symbols. For example, we consider inputs as x, outputs as y, and m as the number of data in the training set. Each row of this table is a sample that contains an x and a y. Since learning is supervised, we have x and y. If we want to refer to a particular sample or input or output, we use the index j. Suppose we give this table, which is the training set, to a training algorithm as input. Now we want to learn a function. That is, the output of this training algorithm is a function. Why have we used the letter H? Because it is the beginning of the word hypothesis. Historically, we name it like this. With the help of this function, we can predict the output for each new input. So we have two phases, training phase and estimation or testing phase. Now the question is, how can this function be shown on the computer? Be careful that the computer is supposed to do these things. Here we have exactly the same classic line equation, and our x is the input x, and we call y h as h here. This function is a parametric, and we can change these thetas. To show this parametric nature, we put this theta as a subscript of h, and this h has no other meaning, and this theta has no other meaning. What we can change is this theta. X's cannot be changed. This is a single variable linear regression problem because real numbers are the outputs of this function. This function is linear and scalar, and we have considered one dimension. We have not considered the location of the house, its construction, and the other dimensions. A very important concept in problem solving is the cost function. This function determines which hypothesis is better. So to specify the function h, it is necessary to specify theta 0 and theta 1. So we have to learn these two parameters. The question is how to learn these parameters. These two parameters can be in the range of negative infinite and positive infinite. We want to know what is the best value for these parameters. The role of theta 1 and theta 0 is very simple. They determine the slope and width from their origin, from the center. The distance from the center, actually. Center of the Cartesian axis, coordination axis, the Cartesian coordination axis, the center of here. Suppose we have three ways here. Which hypothesis is better than others? It is clear that the best hypothesis is the second hypothesis. The first hypothesis is very bad. The third hypothesis is better than the first, but not very good compared to the second. You can easily recognize this, but the computer needs numbers for this diagnosis. So we have to evaluate this hypothesis numerically. We should be able to determine the size of good or bad, the amount actually of goodness or badness. We want to define a function that determines how bad the hypotheses are. We call this function the cost function, which is one of the main components in any machine learning system. This function has different names. In this training course, it is called cost function. In some other sources, it is also called the loss function or closed function sometimes. Both of these names refer to the same concept. The cost function is not specific to regression and is used elsewhere. Suppose that for specific data, for example, JSON data, we have this form. We want to perform calculations so that the distance of this data from the linear function h is small, is very little distance, a very low distance. That is, we want to calculate theta 0 and theta 1 so that the distance of our training data from the h function line is minimized. We want to have the closest possible hypothesis function to the original data. Obviously, we have to do this numerically. For each value of x and for each value of x, we have two values. One is the value provided by the training set itself, and the other is the value that the h function estimates for us. The difference between these two values is the error value. This value, this error value actually can be calculated for all data. We raise these errors to the second power, and actually we squarized these errors and add them together. We calculated the sum of the squared errors here. The result is called the function of the set of error squares actually. This is our cost function, and the lower the final value of this function is, the lower our cost is. Mathematically, this half of 1 divided to 2, this number, this 1 divided into 2 factor has no reason and has no effect on evaluations. Rather, it is placed due to the reduction of the computational load and has no other effect. We will talk about these details later. Obviously, this function never becomes negative, so we need to minimize this function. That is, get the values of theta 0 and theta 1 so that this cost function is minimized. In this way, we can get the best possible hypothesis. The discussion of community building is a discussion that has already existed in mathematics. The discussion of actually minimization, maximization, and getting to the optimum point is a familiar discussion in mathematics. For simplicity, let's assume that the function h has one parameter, that is, we consider theta 0 as a 0. We did this to make drawing the shape easier. First, we consider that theta 1 is equal to 1. The output is 1. Our prediction is also 1. So the error or our cost function is 0. Now we can plot the j function itself in terms of theta 1. To draw this function, we remove the theta 0 to make it easier to understand. For some other points, we want to get the value of the cost function so that we can draw the j function as well. We see that for theta 1 equal to 0.5, I mean a half, the value of j is equal to 1.75. You can also see that for theta 1 equal to 0, the value of the cost function is equal to 7. Okay, you can say this here. Okay, you can see this here. For theta 1 is 0, the value of j is equal to 7. With the help of these points, we draw the j function in terms of theta 1, and you can see the result here. Okay, in the next video, we will continue these concepts. I don't want to bore you and make you tired. So, see you in the next video, and wish you a happy time. Have a nice time.